Hey guys, my name is Hiraku Murakami, back with another video with NovaEdge Academics. Today we'll be continuing with topic C4. Now, until last part, part 1, we've covered strings and standing wave caused by transverse wave and a bit about sound standing wave. Today we're going to cover sound standing wave in a pipe. Okay? Now there's 3 patterns possible for a sound standing wave in a pipe. There's a pipe that's both open-ended. There's a pipe where there's only one end open, and there's one that's just enclosed. You might be saying, how does sound propagate through these and how do they reflect? Because remember, standing wave occurs because there's a reflection and 2 waves superpose each other and causing this phenomenon. Well, this is pretty simple, right? If I make sound into the pipe, it bounces back and boom, there's a standing wave. How about this guy? Well, if I just vibrate the pipe, then that vibration causes air to vibrate back and forth, back and forth. How about open-ended? That's a little bit tricky and it's actually outside the scope of IB, why that happens, but just know that sound can also reflect even if the pipe has an open end on both sides. And this is due to pressure at the end of the pipe and how pressure is released and there's like a knockback effect. You don't need to know this. Just telling you that there is standing wave happening in all 3 of these, okay? Now, one thing to note is that antinode is always at the opening end and node is at the closed end. This is really important. I'm going to show it to you, okay? So let me show you all those like first, second, and third, and fourth harmonic that we've been talking about for string wave pattern. Now we're going to do it for the pipe. Okay, so let's do the first, the first open-ended one. So in the first harmonic, it looks like this, okay? Now, remember I told you that for the open-ended, it's always at antinodes. So this guy is antinode, this guy is antinode, right? This is a requirement. So when we draw the first harmonic, it looks like this. Now, one thing to remember is we need to be able to mathematically derive frequency and wavelength, right? So if this was length L, what is a wavelength? Well, you need to be able to count how many waves there is in that specific pipe. So, how many is there? This is just half. If I go from here back to the top, that's 1 full wave. But there's half a wave, right? So, what is a wavelength? Wavelength, the distance of 1 full wave is equal to 2 times length L. So, this is actually the exact same as what we had before. So, frequency will also be, okay? How about second harmonic? It will look like this. Again, same thing, wavelength is length L, frequency is V over L. How about third? Again, 1 full wave will be here, right? And then you have this. So what does that look like? This will be 2 full waves, right? So this is like 1.5 or 2 over 3, 2/3 of a length L, okay? Now, I hope you're able to see this. It's a bit difficult because of my drawing, but this is 1 full wave, and then you have half a wave here. Half, right? So essentially 1.5 times wavelength is equal to L, or wavelength is equal to 2 over 3L, okay? Frequency, of course, is velocity over this. All right? You have to be able to derive this when you draw it, okay? How about when you have both ends closed? Well, it's the same thing as a string that we did, right? First harmonic. So it's going to be exactly the same. I'm actually not going to cover this because I don't want to make the video too long, but it's exactly the same as when we did string in the last video. How about if you have one end open? So remember, the opening has to be antinode and the close has to be node, right? So if I have this, it looks like that. Now this is actually quarter of a wave, okay? So basically, this is the first harmonic, by the way. This length is equal to quarter of a wavelength. which means wavelength is equal to 4 times L. Okay? Frequency is V over 4L. How about second harmonic, you might ask? Well, this is a bit of a trick question because when you have one pipe end open and one closed, you actually don't get a second harmonic. You get third harmonic. You go straight to third. And this is how it looks like. So now you have 3/4 of a wave. Okay, do you see how important it is to be able to draw it? Because when you draw it, I'm able to visualize how many waves there are and derive the equation. Okay, so now this way I know that length L is equal to 3/4 of a wavelength, or 3/4 of a wave. Okay, in that case, one wavelength is equal to 4 over 3 length L. So frequency is V over this. Okay, how about fifth harmonic? Well, let me try to draw it. It would look like this. So this length L has one wave and a quarter. So length L is 1 wave and a quarter. So wavelength is equal to 4/5 of a length. And the frequency is V over this. Okay? Really important that you're able to draw this out, because without drawing it, I would make a mistake, especially during the exam when you're stressed. Okay, so make sure you're able to draw it out and derive it on the spot. This is too many to memorize, right? So now I'm going to show you a very popular application of this, and of course problems that come with it. Okay, so a very popular question that they can ask you is that they have a vibrating fork where they do ding 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 and it creates a frequency of sound, right? And they have this open-ended pipe submerged in water. Now what happens when it's submerged in water? This surface acts as a wall. It reflects the sound wave. Okay, so that means you have one end open and one end closed pipe wave pattern forming. Okay, now why is this important? Because they can actually change the position of the pipe so that you have more length. You can vary the length from length 1 to length 2. Okay, and they'll pretty much usually give information like this, where they tell you the length 1 and they tell you to find length 2, which is the third harmonic, right? Or some variations like that, or like find a frequency when they give you both length 1 and length 2. Stuff like that. Okay, so let's do an exactly the same practice problem. Okay, so pause the video, give this one a try. Okay, so they gave us speed and they gave us frequency. Okay, so we know in a wave pattern for the first harmonic, let's draw it out, right? This length L is equal to 1/4 of a wave. So wavelength is 4 times length L, right? And now we're able to calculate the wavelength because they give us both the velocity and the frequency. And now I can show you that the length for the first harmonic, L1, is equal to 1/4 the wavelength, which is like that. Okay? Part B, how far will the pipe need to be raised until the next harmonic is heard? Okay, what is L2 essentially is what they're asking. Let's draw it out. Second harmonic looks like this, right? So you have, this would be the full wave. So that's 3/4 of length L is equal to wavelength. Okay, so L2 is equal to 4 over 3 lambda, which is 1.19 meter. That is length 2. So how much do they need to raise it? 1.19 minus 5.22. They need to raise it by 0.97 meters. So this is 0.97 meters in order for the next harmonic to be heard. Okay, very, very popular question. It will definitely come up in your paper exam, in your final exam, and also your topic test. So now that we've talked about those pipe wave pattern, let's talk about boundary conditions. And this boundary condition, I'm mentioning this because it's in the textbook. It just means conditions at the boundary. Pretty simple, right? A lot of people get confused what boundary condition is because it sounds like a fancy word, but it's not. It just means the condition at the boundary. So for us, this is basically whether it is open-ended at both sides or open-ended at one side or closed at both sides. That is called boundary condition. Mathematically, though, there is boundary condition as well, not just qualitative boundary condition. Boundary condition can just tell me, basically, at x equals 0, this is x equals 0, maybe x equals L, right? At x equals 0, what is the amplitude? Amplitude could be max. It is actually max because it will look like this, right? At the open end, we always know it's an antinode, right? So you can mathematically express it, okay? So that's just boundary condition. Very simple. You might hear it in university where a boundary condition is used to derive equations or something like initial conditions. These are something that you'll encounter at the next level. For now, boundary condition just means condition at the boundary, and you can qualitatively say so that it's open-ended pipe. Now, next thing, what is natural frequency? Well, natural frequency is just the frequency of oscillation that materials naturally oscillate at. In fact, we take advantage of this in the guitar. So in the guitar, I told you that how many harmonics it vibrates at or oscillates at. Also, frequency depends on the length of the string, the weight of the string, and the tension of the string. If we change the tension by tuning, it changes the sound. If I place my finger closer to or move my finger, it changes the length of vibration, right? Or if I change the weight of the string, like using this string versus that string, it changes the frequency again, it changes the pitch again. So natural frequency just means oscillations, frequency of oscillations that materials naturally oscillate at. And we take advantage of this in musical instruments. Next thing, what is damping? I'm explaining these concepts because you need to know. Damping is a dissipation of energy due to resistive force, okay? And it's basically stopping the oscillation from happening. And there's 3 types. There is lightly damped, heavily damped, and critically damped. A perfect example of lightly damped system is a pendulum. A pendulum is not perfect. We've been assuming it to be perfect where there is no air resistance. But in fact, there is air resistance. And after a while, it stops, right? It stops, comes, and you have 0 amplitude. That is what lightly damped does. Next, you have critically damped and heavily damped. Heavily damped just means that the oscillation becomes really slow, really slow. In fact, it will take forever until it reaches amplitude of 0. It comes back to equilibrium. Critically damped is an extent of damping where this oscillation comes back to its equilibrium at its fastest rate possible. That is what critically damped means. If I were to order these, heavily damped out of 10 is, let's say, 9. Lightly damped out of 10 is 1. Critically damped would be like 6 or 7 on that scale, okay? And I actually will show it to you like on visual right now. I'm going to use this toothbrush I was meaning to throw away. If I were to lightly damp it, I'm not going to put any strength. It's just going to bounce back and forth until it comes back. Perfect, right? If I were to heavily damp it, I'm just going to pinch it stronger so it just refuses to come back to the center. This is heavily damped system. Okay? How about critically damped? I press it strong enough that it will come down, but it stays at below. It doesn't oscillate back and forth. Like that. Like that. Okay? So that is what critically damped is. So now you know lightly damped, then critically damped, then heavily damped. Okay? Last but not least, what is resonance? Resonance is a phenomenon that occurs when displacement increases due to you applying an external force at the system's natural frequency. A lot of fancy words there, right? Let's break it down. What does it mean? Basically, if you have a child on a swing, probably the father or the mother is at the back pushing the child, right? Now you push the child at a certain frequency, that this swing naturally oscillates at. And when you do that, you increase the displacement of the child's swinging. That is called resonance. Or a second case like this, you probably maybe seen it in TikTok. I've seen it recently, right? It's where they have this water bridge swing battle. So they have a bunch of people at the two edges. They have a challenger in the middle, and the challenger's whole objective is to stay on the bridge. And the objective of these guys is to swing it so fast and so much that this guy loses balance and falls. What they do is they use a weight at the appropriate time. They push the bridge at the appropriate time to keep swinging it and increasing this displacement until the challenger fails, right? This is called resonance. Now, that's all fun, right? But resonance can be a bad thing. In fact, we have some bridges and infrastructure that breaks down because of resonance. So, for example, this Tacoma Narrows Bridge in 1940. What happened? Well, the wind kept hitting the bridge at the right moment, okay? At the naturally swinging frequency of the bridge, because the bridge, as stationary as it looks like, it swings a little bit. And when the wind hits it at the right time and keeps on hitting over time, the bridge actually was twisting. And that twisting over time caused it to completely collapse. This is also really, really common in like earthquakes, right? In Japan, for example, where I'm from, buildings oscillate with the earthquake. It's designed to sway and swing so that it doesn't just take all of the damage and absorb all of the inertia, right? But what engineers have to be careful of is is making sure that the building doesn't swing at a certain rate that matches the earthquake shaking below. Because if it matches, it's going to cause resonance and it's going to catastrophically increase the displacement until it breaks. Okay? So that is a concept of resonance. And this is the end of topic C4, standing wave. So if you found this useful, then give us a like and comment, and we'll see you in the next video where we talk about Doppler's effect in topic C5.